Today we're going to drop the basketball first from a height of 1.5 meters. This is what's going to happen. Now we're going to drop the tennis ball from 1.5 meters. Now we're going to drop a wiffle ball from the same height of 1.5 meters. So now this is where the actual experiment comes in. You've seen how all the other balls bounce and what height about they bounce at, but what happens when you put one ball on top of the other? Well, the kinetic energy from the basketball when it falls will transfer into the tennis ball because the basketball decompresses slightly when it hits the ground, but recompresses. That's why it bounces. The tennis ball is going to be in contact with the basketball the whole time, and the tennis balls bounce on their own, so it's got the tennis ball's own kinetic energy. So when you combine the two, the basketball transfers all the kinetic energy into the tennis ball because when it reforms, it's going to hit the tennis ball, meaning the basketball isn't going to jump as high, and the tennis ball is going to go much higher than it originally did, just like this. Now I'm going to do the same thing with the wiffle ball on top of the basketball. It should give us similar effects to what happens with the tennis ball, just like this. Now, I've put the wiffle ball and the tennis ball on the same experiment. Now, because what happened last time was the kinetic energy from the basketball transferred into the wiffle ball and the tennis ball respectively for each experiment. Now, however, because the wiffle ball is on top of the basketball, but the tennis ball is on top of the wiffle ball, all the kinetic energy will transfer into the tennis ball from the basketball and the wiffle ball straight through to the tennis ball, meaning the tennis ball is going to go a lot higher than it did previously. Just like this.
Here's the data for how to find how high the tennis ball ended up going. We started with the position function with an initial height of 1.5 meters, a final height of 0 meters, and a 0 initial velocity, giving us just the acceleration of negative 9.8 meters per second squared. Solving for t, we end up with 0.553 seconds. Then, using the equation v equals at, we solve for v to get negative 5.422 meters per second. We then plug that into the kinetic energy formula for each of the three balls, the tennis ball, the wiffle ball, and the basketball. We add these values together to get 10.7083 joules. Setting that equal to 1/2 mv squared kinetic energy, we can find the velocity of the tennis ball. Solve just by multiplying by 2 and dividing by 0.0585, the mass of the tennis ball, we find the velocity of 19.1336 meters per second. Finding the average time, then, using the average velocity, we end up with t equals 1.9524 seconds. Then, using the position functions once again, y equals 0 plus 19.1336t plus 1/2 times negative 9.8t squared. Plugging in our value for time, we end up with a height of 18.6783 meters. This collision with the three balls, the basketball, the wiffle ball, and the tennis ball, is an elastic collision, meaning that the kinetic energy from the basketball and the wiffle ball are both transferred into the tennis ball, which is why it goes flying up into the air. But how is this happening? Well, when the basketball hits the ground, it decompresses into form slightly, becoming a bit flatter. This is the moment when it is no longer into contact with the wiffle ball. The wiffle ball then comes into contact with the basketball, which is not recompressed yet, and then it decompresses as well as it comes into contact with the basketball. This is also the moment when the wiffle ball is no longer into contact with the tennis ball, as it has decompressed. The tennis ball then comes into contact with the wiffle ball, which is already being recompressed by the basketball. Now, the basketball's recompression is already launching the wiffle ball higher into the air, but the tennis ball there is to stop it. So, the basketball recompresses, giving the kinetic energy of itself into the wiffle ball. The wiffle ball then recompresses, sending the kinetic energy from both the basketball and itself into the tennis ball, which is why the tennis ball goes up about 18.7 meters higher than it would in this experiment.
Alright, now I'm going to show an inelastic collision by dropping an egg from the same height of 1.5 meters, just like this.
The egg dropping is an inelastic collision, in contrast with the 3 balls stacked on top of each other, each of which was an elastic collision. This means that with the egg, the kinetic energy is not conserved. Why is this? Well, the balls, the reason why the kinetic energy was conserved was because when you dropped them, they decompressed when they hit the ground and recompressed, launching themselves back up into the air, or launching the other balls back up in the air in the case of the basketball and the wiffle ball launching the tennis ball up. With the egg, however, once it comes in contact with the ground, the shell is too fragile and too brittle and it just shatters, launching the contents everywhere, which means that the kinetic energy is not transferred.